Hello students. In the previous lecture, we started looking at control dependence among instructions and how that can potentially lead to control hazards. In order to reduce the penalty in performance due to the control hazards, we started exploring some optimizations that we can include at the hardware. What we did was move some uh, computation from the execute stage to the decode stage, basically the comparison uh, operation of whether the values in the registers are equal, not equal, greater than, less than, so on and so forth. The comparator has been moved, and because we would know the outcome of the branch in the decode stage itself, we saved one cycle. And for jumps 2, we said that we can potentially save one cycle. And the question I left you with in the last class was, can we do anything better? We did good by reducing the branch penalty from two cycles to one cycle, but even then, because the number of control instructions in a typical program is quite high, nearly 25 to 30%, uh, we would potentially incur 25 to 30% of loss in the performance. How do we handle that? We need some more sophisticated method. So that's what we are going to look at in the next couple of classes. In order to answer that question, the what we can do better, we should think about what we can do during the instruction fetch stage itself. If we are able to do something in the fetch stage, possibly we can reduce that one cycle also, right? One cycle the branch penalty. But to do anything at the fetch stage is very tricky, because at the fetch stage all we have is the PC of the instruction, right? We don't know whether it would be a control instruction or not, and uh, that is the first question. The second question is, if it is a control instruction, whether it will be taken or not taken. We don't know the outcome of the control instruction. And the third question is, if it is taken, where is its target address, right? All these things, if we are able to answer together, right, that is the optimization that we are going to discuss now, which is called branch prediction. And I have specifically color coded predict here in the second question, because we are not going to resolve the branch here. All we are going to do is make a prediction whether the branch will be taken or not taken. And like any prediction, it can go wrong also. In that case, we have no other option but to flush the pipeline. But if the prediction is correct, then we would save that one cycle, right? So the branch prediction, as the name says, is primarily making a guess, right? An informed guess. And prediction, as you know, is one of the great ideas in computer architecture. It's used at quite a few places, and this is the first example that we are seeing in this course. We are going to look at a couple of them in the next module also, which are based on prediction. Okay, now let's try to answer each of these questions one by one. If we are able to answer all the three, we will know what instruction to fetch next. If we are able to do that correctly, then we will not have any branch penalty. So let's start with task 1 and task 3 first. We'll come to task 2 in the next class. The task 1 is, how do we identify that the newly fetched instruction is a control instruction? All we have is the PC, like I said. Now, to understand what we can do, let's look at a small example. Okay, now here is one small code that we are going to walk through. Basically, it's a for loop, right? I is the iterator, and we will loop n times, and if I is even, right, the value a of I is added to b of I and written to c of I. But if I, or the index of these arrays A, B, C, right, is odd, then what we are doing is B of I is subtracted from A of I and the resultant is written in C of I. Just a simple operation to understand the branch prediction part. Okay. Now I have written the RISC-V code, and here is the assembly code. So in the data segment, we have three arrays: array A, B, and C. All of them are storing elements of size word. So accordingly, we have given dot word. And let's say array A has elements 10, 20, 30, 40, 50, and 60, right? And array B has elements 5, 16, 27, 38, 49, and 51. And I have initialized array C to be all zeros. By default, it will be 0 anyways, but this just for my own convenience, so that we will be able to trace it better. Okay. And in addition to these three arrays, I have also stored the number of elements. Here we have 6 elements in each of arrays A and B, and the resultant array C also will have 6 elements. In the text segment, this is how it would look. I have I got the address of array A and placed it in register X4, address of array B in X5, address of array C in X6, and the number of elements is placed in register X7. And let's say this the register X15 is my iterator I in the high level code, right? The very first value that I will have is 0. That's what line 12 would do. And we would do a comparison whether the value of I is equal to the number of elements, right? In the C code, it would be n. Here it is 6. If they are equal, then we are going to go to exit in line number 28. And in line 28, I just placed dummy instruction just to say that this is the common fall through code. But if the value of I and n are not equal, what we are going to do is we are going to generate the address of A of I and place it in register X10. And using that address, we are going to get the value of A of I and place it in register X11. Again, we are going to get the address of B of I and place it in X10, and we are going to get the value of B of I and place it in X12. At this point, we also generate the address of C of I and keep it ready. The address of C of I is available in register X10 in line number 19. Okay. If you want to avoid confusion, you can use different registers also. And in line number 20, I'm going to look at the LSB bit of X15, right? Basically, I'm ANDing X15, means I with the value 0x1. It will give me the LSB bit, and that will be placed in the destination register X9 here. If the value in X9 is 0, then we are sure that I is even. So in line 21, we are going to do that comparison. If it is equal to 0, then I'm going to jump to line 24, where I'm going to add A of I and B of I, place it in a temporary register X13. And in line 25, we are going to write whatever is there in X13 into the location C of I. But if the value in X9 is 1, meaning that I is odd, we are going to continue and execute x22 because the branch will not be taken. Here we are going to subtract a of I and b of I and place it in temporary register x13, and following after that we are going to jump to the fall through code, which is line number 25. This is common for both add and subtract aspects of C of I, right? Whatever is the value in x13, we are going to write it in the location C of I. After that, we are going to increment the value I, and we are going to jump to the location labeled loop. So that is the beginning of this loop, where again we check whether I and the number of elements n is equal or not. So for I equal to 0, I equal to 1, 2, 3, 4 and 5, the loop will get executed, and when I becomes 6, because they are equal, we will come out of the loop and reach line number 28. So let's look at this execution stepwise, and from there we are going to get an insight for the branch prediction, okay, for the very first question. So let me step through. We got the address of A of I in x4, address of B of I in x5, right, and address of C of I in x7. No, sorry, x6. And x7 has the number of elements here, it is 6. Following that, we are going to initialize I with 0, and we are going to compare it with I think now it's a little better. I is compared with value in x7. Because it's not equal, we are going to continue with the next sequence instruction, which is SLLI, and so on and so forth, right? So this is the way it would go on when I equals to 0, because it is even. Now we will jump to a location which is 12 spaces from here. Which is the add instruction, right? And we are going to store that value in C of 0, increment I to 1, which would be in x15, right? And we are going to jump back to the loop, which is the BEQ. Now here I equals to 1 and x7 has value 6, so we are going to continue the loop, right? And here, because the value of I is 1, x9 will have 1, saying that it's a odd number. So instead of jumping to the location given by the label even, basically instead of jumping to add instruction here, we are going to continue with the subtract instruction, and then we are going to jump to the location which is the fall through code. At this point, we are going to write the value in x13, which is the subtracted value, in the location given by x10, which is C of 1. So this loop will continue for C of 2, 3, 4, 5, right? And eventually it will terminate. That is the flow of the entire program. But what we need to keenly observe here is the locations or the addresses of these instructions are not changing for multiple iterations of the loop. For example, the address of this BEQ is always 0x24. The address of SLLI for I equals to 0, 1, 2, 3, 4, whatever, is still 0x28. The address of let's say pick this control instructions BEQ x9 x012 is always 0x44. The address of any instruction does not change when it is being when it is being executed. Only at the compilation time, right? If you make any changes in your high level program, your compiler will do appropriate changes in the assembly code and eventually generate the machine code. And in the machine code, each instruction is given a specific address. That's what we are referring to as PC. Now let's go back to the question that we wanted to answer. How can we identify that the newly fetched instruction is a control instruction, right? Because the PC is fixed for an instruction, the very first time we might not know that the instruction which is fetched is control instruction, but when it is getting decoded, we will know that it is either the branch or jump instruction, right? At that point, if we keep a copy of this PC, then the next time when this instruction is getting fetched using its PC, we can compare it with our table or whatever you want to refer it as. And if there is a match, then we surely know that the instruction we are fetching is a control instruction. So that is the answer for our first question. We will use the PC to identify whether the next instruction that we are fetching is a control instruction or not. Okay. Now let's look at the third question, which is how do we know the target of this control instruction? Yes, using PC we have identified that it is a control instruction, but can we know where it's going to? Again, let's look at the example and get some insight. So let's take this particular instruction BEQ X9 X012, right? If you look at its address, it is 0x44. This is fixed, and the very first time we executed BEQ or we fetched BEQ using its PC 0x44, we don't know it's an branch instruction or a jump instruction in general. We don't know what instruction it is in the fetch stage. That we are going to know only in the decode stage. We are going to look at its opcode and identify that it is an control instruction. And so we will keep a note of this PC. That is the task 1. In task 3, we want to know where this BEQ would jump to if it is taken, right? Again, if we note, the value 12 will never change, right? It will always, if the branch is taken, it will always jumps by 12 places and reach 0x50. So the very first time we are executing the BEQ, right? If it is taken, we will know the target address. Just like the PC is fixed, the target address is also fixed. The same way for the JL instruction also. JL, the PC here is 0x4C, and when we execute it, we will know that it needs to jump by 8 spaces and it will go to 0x54. So we will store 0x4C and 0x54 to say that 0x4C is the PC and 0x54 is its target. So that's how we would be answering the third question. How can we know its target? The very first time we execute, right? If it is jump instruction, we will know where it has jumped to. We'll keep it ready. If it is a branch instruction, we need to know whether the branch is taken or not. If it is taken, then we will know the target address because we are going to calculate that. So what we basically are doing is we are making a note of the PC and the target. Both of these are addresses. So at the fetch stage, effectively, we will store the PC of all the control instructions, and we will also store the target address for each of these control instruction. For jumps, it is more or less a trivial task now, right? We will know that in the fetch stage, right, the instruction that we are getting is a jump or not, because we are making a note of its PC, and because we also know the target. In the very next cycle, instead of fetching the next sequential instruction, we will fetch from this target location. So the branch penalty becomes 0 for the jumps. But for branches, it's a little tricky. Yes, using the PC, we will know that it's a branch instruction, but we are making a note of only the target address of its previous execution, right? Previous instance when it has executed. Now let's say in the previous instance it was taken, so we make a note of the target address. But in this instance, based on the values in the registers, right, it might not be taken. So in the example that we saw, if I equals to 0, it has jumped to some instruction, right? That is the target instruction. But the next time we are trying to execute the same instruction, the value of I is 1. So the output of this branch is not taken. So instead of storing one address, probably we need to store two addresses, right? Because the next instruction, if the branch is taken and not taken, are different. So we need to make a note of both the addresses so that we will pick one of them. How we pick one of them is the task 2, where we are trying to make a prediction. Okay, if the prediction says this time the branch will be taken, we'll go and take the target address we saw earlier when it was taken. If the branch prediction says this time it will not be taken, then we will go and pick the address which is stored, which we got the last time it was not taken. Okay, that's how we would handle the scenario based on the prediction. If we make a store note of both taken address and not taken address, our life would be simple. But are both required? That is an interesting question, because if the branch is taken, yes, we definitely need to make a note of where we are jumping to. But if the branch is not taken, what we do is we move on to the next sequential instruction, right? So if the branch is not taken, we don't need to explicitly store the address, because where it will go to is PC plus 4, right? Now, if we look at the hardware that we need to address task 1 and 3 of branch prediction, it would look something like this. It's called branch target buffer. It will have multiple entries. Imagine that it's a array, right? Or just like registers, we have a set of entries in the branch target buffer, right? Each entry will store the PC of the control instructions and the target address if it was taken. And how do we index to this BTB? We use the PC itself. In the fetch stage, when we send the PC to the memory, right, to get the actual instruction, we are going to use the same PC to index into the BTB. If there is a match in the branch target buffer, then we will know that yes, it is a control instruction. And if it is a control instruction, because we are storing the target address also, we'll take the target address and start fetching from there in the next cycle. If the branch prediction says it will be taken this time also, right? So in the previous example, the line number 14 had instruction with label loop, and the target address, if it is taken, is line number 29. In line 22, we had BEQ. If it is taken, it would go to line 25. If the two additional instructions we had were the jump instructions, in line 24 we had JAL, and its target, which is always taken, is line 26. Another control instruction we had was L28 and its target was L14. Now the very first time we are uh, executing all these instructions when I equals to 0, that's when in the decode stage we will know that whatever instruction is there in line 14 was uh, a control instruction, and at that point we'll make an entry in the BTB, and when this instruction goes to the execute stage we will know the outcome of the branch, and if it is taken we will go and update the same entry in the BTB with its target address. The same thing would happen for the other entries also. The very first time they get executed, we'll not be able to find a match in the BTB because at that point we don't know that there were control instructions. But from the next instance onwards, because their PC will be stored in the BTB, we will know that it's a branch or jump instruction and what would be its target address. Right now, to replace the line numbers with exact PC values, it would be like this. The first BUQ instruction, its PC was 0x24 and the target address, if it was taken, is 0x60. And the second BUQ instruction's address was 0x44 and its target PC was 0x50. The first JL instruction we saw, its PC is 0x4C and its target is 0x54. And the last control instruction was again JL. Its PC is 0x5C and target PC is 0x24. So this would be the entries on the BTB as we keep executing that particular program. Okay, using this BTB in the fetch stage itself, we will know whether the instruction we are fetching is a control instruction or not, and if it is a control instruction, what would be its target address. So some of the design challenges in the BTB or would be how long should this BTB be, right? Some programs can have fewer number of control instructions. Some other programs can have large number of control instructions, but BTB is a hardware module. We can't change it dynamically, right? So at the hardware, when you are fabricating the chip, how long should the BTB be? Should it have 10 entries, 20 entries or 100 entries? This is a design challenge that architects try to answer. And the other design challenge is if we have the entries in the BTB which are lesser than the control instructions we have in the program, how to deal with it. For example, let's say we have created in the hardware, or we have fabricated the BTB with only 10 entries. Now let's say my program has 20 control instructions. In that case, how do we handle? Right? Even though I'm able to identify all the 20 control instructions the very first time that I execute, I can keep only 10 of them at any given moment in the BTB. So it has a negative impact on the performance also, because when the PC is checked, right, if it is not part of the 10 instructions that we are storing in the BTB or the 10 PC that we are storing in the BTB, we will not be able to make a guess whether it is a control instruction or not. So the task 1 itself will get unanswered, right? Forget about task 3 anyways. So this the size of the BTB is a very tricky design choice. Now the direct answer would be, why don't we make a very large BTB, right? Let's say we make a BTB of 1024 entries. But even then, some program we can write which has more than 1024 control instructions. But let's say the program still has fewer instructions, then the BTB is sufficient. But the catch is, we want the output from the BTB within that excuse me, within that fetch cycle itself, because by the end of fetch cycle excuse me, we need to know whether the PC is a control instruction, right? And if it is a control instruction, where the target is, because in the very next cycle we are going to use the target and start fetching. So if your BTB is longer, it is more likely to take longer time to index into the BTB and get an output. So this is a tricky choice. Okay, with these questions, I will pause this lecture, and in the next lecture we are going to look at the actual branch prediction, the task 2 of the branch prediction. Okay, thank you.